So hello everyone, my name is Devan Sharma and I work for Tessent Embedded Analytic team at Siemens EDA. Today I'm going to talk about leveraging the RISC-V efficient trace standard. Firstly, I would like to thank my colleague Ian Robertson for his work for these slides. And in this presentation I'm going to talk about why do we need trace, that's the first question. And then talk about the RISC-V efficient trace standard, followed by comparison whether this trace standard is, how efficient this trace standard is. And then in the later part, I will basically conclude with my observations. So the big question is, why do we need trace? So if you think about it, the SOCs are getting complex, and so is the software programs which are running on these SOCs. So to observe, what exactly is happening with your software, and to observe its behavior on how it's going to basically work on the SOC, it's going to be very, very challenging job. So in order to basically make this, little bit easier, trace is required. And second thing is, think about some heterogeneous system where you might have CPU to CPU interaction going on, you might have some real-time events happening. In those cases, the traditional way of debugging might not be sufficient. So in case of real-time events happening, you want to monitor that at full speed, and then only you will be able to basically get the real behavior of the device. So thirdly, what is required is the observation at full speed. That means what you are looking for is the ability to capture the instruction executed on the CPU. And then ability to basically do some sort of compression so that you don't have to provide a lot of data off chip as well. So the high encoding efficiency is important as well. So processor trace provide you that sort of capability. So in nutshell, what we can say is processor trace provides you the visibility. In addition to the visibility, what it also does is it gives you capability to do code profiling, code coverage, find some sort of bugs, which might not be regular bugs, Heisenberg bugs, and that sort of thing. So now I'm going to talk about, how does this encoding mechanism work for RISC-V efficient trace standard. So what it does is it basically make use of processor branch trace. What happens in processor branch trace is trace begins by reporting the start address of the program, and then all the branch instructions, which basically alters the normal execution of the program, are reported in the trace log. The normal instructions like move, add, these are treated to be sequential instructions, so they are not reported in the trace log. So what we report in trace data is whether a branch is taken or not. And finally, some of the indirect jumps or where the normal flow of the program is disrupted, the destination address must be reported. Let's walk through an example. So here you can see we have a assembly language program. So trace begin by reporting the start address of the program, which you can find in ELF files, when you are doing the software development. Then next two instructions are, the sequential instructions. So they are not reported in the trace sequence. Then the following instruction is the branch instruction. Now we don't report the branch instruction. What we report is whether a branch is taken or not. So in this case, branch is not taken. So that's why, we are reporting the branch not taken. And then, then there are some sequential instructions which are not reported. And then followed by a branch instruction. Now this time the branch is taken. So hence what we are reporting in the trace log is the branch taken instruction. And then the loop goes around, and next time you basically come to the branch instruction, this time the branch is not taken. So that is also reported. So here in kind of a green block you can see that's the kind of the compressed information you get out of processor branch trace basically. So now talking about RISC-V E-trace standard, firstly I would like to mention that the initial specification for RISC-V efficient trace standard was donated by Siemens, and these were refined and ratified by RISC-V International. So efficient trace for RISC-V covers basically the encoding mechanism for instruction and data trace. It also covers the the CPU to trace hardware interface, and then there are some optional instructions, optional features which are also included in this standard. I think what is very unique about this trace standard is that our relationship with the RISC-V is quite long and deep. So we have been working with RISC-V efficient trace standard for quite some time now. So the question is, how does it compare with some of the solutions which are present there? So this is basically, this slide provides you the efficiency of the RISC-V efficient trace standard. Here you can see what we are representing is the bits per instruction in terms of the efficiency of the encoding mechanism. So you can see the RISC-V standard is very, very efficient. So what it means in practical terms? So in practical terms, you are achieving higher compression. So when you have higher compression, you are able to trace more. So what it means? So what it means is, let's say you have a multi-core architecture, whereby you have some number of cores. You wanted to basically trace all of them simultaneously. So if you have higher compression ratio, you will be able to get that sort of thing covered, and you can trace for longer. And CPUs nowadays are getting very fast. So how do you make sure you will get the trace for these fast CPUs? So if you have higher compression ratio, you will be able to trace faster as well. And then less bandwidth will be required to send this data off chip as well. So here I'm gonna talk about some of the eTrace features. So there are basically some mandatory features which are instruction trace, hard to encoder interface, delta address trace mode, and efficient packet format. And there are some basically which are optional features which can further enhance the compression mechanism, and then followed by one particular feature which is cycle accurate trace feature. So this cycle accurate trace feature is exclusive to Siemens offering in enhanced trace encoder. So what it means is you can monitor not only what is happening at the CPU, but at what time it is happening. So with the cycle accurate trace feature. As I mentioned, with the optional features, you have the capability to basically get the higher compression ratio. So in this slide, what I am doing is comparing basically trace compression with the optional features and without optional features. So you can see the result is varying. So that means you can, on average, if you average it out, you can get 40% improvement on BPI. Basically, if you use the optional features, so you will get higher compression there. So in conclusion, what I wanted to basically say, the understanding any system and software behavior is very challenging. Efficient trace provide you the mechanism to observe non-intrusively how your CPU core is behaving in real time, and understanding the behavior of the system is even complex. Where at Siemens we basically have monitoring IPs which will allow you to do not only the RISC-V cores trace monitoring, but also overall system complexity as well. We can provide a lot of visibility, and that too by non-intrusive mechanism. So you can learn more. We do have some videos on our website which you can basically use. Here you can see there is one video for where we discuss about the Seagate's case study about the RISC-V and also the Siemens IP, how they can help you monitor your system. Thank you. Thank you.